Hello, my name is Brian Lefevre and I am a senior studying nuclear engineering here at the University of Michigan. Right now I'm standing in the lambda cube laser lab here at U of M. The lambda cube laser can reach intensities of up to 5 times 10 to the 18th watts per centimeter squared. To give some perspective, the threshold intensity that can cause retinal damage is only 2.5 milliwatts per centimeter squared. Even though this laser operates at very high intensities, it does so at just a few watts of power. This is because all that power is concentrated into an ultra-fast pulse, just 30 femtoseconds in duration. I'm in this lab because this past summer I've taken part in Michigan's Summer Undergraduate Research and Engineering program. I've been assigned this research position under the guidance of Dr. Carl Krushelnik and Professor John Neese. My project entailed using the ultra-fast lambda cube laser to machine cavities that are just a few microns in size. I wanted to figure out if, without moving the target or laser, we would be able to produce a cavity with a small opening on the surface, but a much larger volume on the inside. This could then be used for tests involving black body radiation. All incoming energies will be absorbed and emitted as thermal radiation, which is what we hope to achieve for future studies. The target material I chose to machine was aluminum, based on its workability and likelihood to provide sufficient results. From the start, we knew that metal targets would be ideal for machining process due to their thermal properties, and previous research papers had already provided us with some idea of the ablation rates and threshold intensity for machining aluminum. Through varying the intensity of the pulses, I was able to manipulate the size and shape of the cavities produced, adding the ability to run pulses through hundreds of repetitions, and I now have a couple of variables I can use to my advantage in the machining process. Because we're dealing with results on the micron scale, I had to use some specialized equipment to view the cavities. This took me to the electron microbeam analysis laboratory here at U of M. There I got trained on the scanning electron microscope as a method of viewing my results not just from above, but at an angle as well in order to get perspective on the depth of the cavities. Manipulating the intensity and repetitions, I obtained an idea for the magnitude of damage that several variable combinations produced. Here are a couple of images of my results through the scanning electron microscope. Both of these were machined with a laser intensity of 2 times 10 to the 15th watts per centimeter squared, slightly above the damage threshold for aluminum. As you can see, after 100 pulses at this intensity, we have a very small depression, maybe a few microns deep. I increased the repetition to 1,000 pulses at this intensity, and we have a much more defined cavity with steeper walls. This more resembles the damage spectrum we want to operate at in the machining of the bulb-shaped cavity. By the end of my summer research, I was not able to produce a cavity that acts as a black body, but I still feel that I made some progress and learned a lot through the experience. I would like to thank Dr. Carl Krushelnik for the opportunity to work on this project, and Professor John Neese for working closely with me during my research.